Hello everyone, welcome to today's session. In this session, we will talk about Q learning. So, what is Q learning? For a robot and the environment is a place where it has been put to use. Now remember, this reward is itself the agent. For example, an automobile factory where a robot is used to move materials from one place to another. Now the task we discussed just now has a property in common. Now these tasks involve an environment and accept the agent to learn from the environment. Now this is where the traditional machine learning phase and hence the need for reinforcement learning. Now it is good to have an established overview of the problem that is to be using the Q learning or the reinforcement learning. So, it helps to define the main components of a reinforcement learning solution, that is the agent, environment, action, rewards, and states. So, let's suppose we are to build a few autonomous robots for an automobile building factory. Now, these robots will help the factory personnel by conveying them the necessary parts that they would need in order to pull the car. Now, these different parts are located at 9 different positions within the factory warehouse. The car parts include the chassis, wheels, dashboard, the engine, and so on. And the factory workers have prioritized the location that contains the body or the chassis to be the topmost, but they have provided the priorities for other locations as well, which we'll look into the moment. Now, these locations within the factory look somewhat like this. So, as you can see here, we have L1, L2, L3, all of these stations. Now, one thing you might notice here is that there are little obstacle present in between the locations. So, L6 is the top priority location that contains the chassis for preparing the car bodies. Now, the task is to enable the robots so that they can find the shortest route from any given location to another location on their own. Now the agent in this case are robots. The environment is the automobile factory warehouse. So let's talk about the states. The states are the location in which a particular robot is and in the particular instance of time which will denote its states. The machine understands numbers rather than letters. So let's map the location codes to number. So as you can see here, we have mapped location L1 to state 0, L2 state 1 and so on. We have L8 as state 7 and L9 as state 8. So next, what we are going to talk about are the actions. So in our example, the action will be the direct location that a robot can go from a particular location. Consider a robot that is a L2 location and the direct locations to which it can move are L5, L1 and L3. Now the figure here may come in handy to visualize this. Now, as you might have already guessed, the set of actions here is nothing but the set of all possible states of the robot. For each location, the set of actions that a robot can take will be different. For example, the set of actions will change if the robot is in L1 rather than L2. So, if the robot is in L1, it can only go to L4 and L2 directly. Now that we are done with the states and the actions, let's talk about the rewards. So the states are basically 0, 1, 2, 3, 4, and the actions are also 0, 1, 2, 3, 4 up to 8. Now the rewards will be given to a robot if a location which is the state is directly reachable from a particular location. So let's take an example. Suppose L9 is directly reachable from L8. So if a robot goes from L8 to L9 and vice versa, it will be rewarded by 1. And if my location is not directly reachable from a particular equation, we do not give any reward, a reward of 0. Now the reward is just a number and nothing else. It enables the robot to make sense of the movements, helping them in deciding what locations are directly reachable and what are not. Now, with this queue, we can construct a reward table which contains all the required values mapping between all possible states. So, as you can see here, in the table, the positions which are marked green have a positive reward, and as you can see here, we have all the possible rewards that a robot can get by moving in between the different states. Now comes an interesting decision. Now remember that the factory administrator prioritized L6 to be the topmost. So how do we incorporate this fact in the above table? Now this is done by associating the topmost priority location with a very high reward than the usual ones. So let's put 999 in the cell L6, L6. Now the table of rewards with a higher reward for the topmost location looks something like this. We have not formally defined all the vital components for the solution. We are aiming for the problem discussed. Now you will shift gears a bit and study some of the fundamental concepts that prevail in the world of reinforcement learning and Q learning. First of all, we will start with the Bellman equation. Now consider the following square rooms, which is analogous to the actual environment from our original problem, but without the barriers. Now suppose a robot needs to go to the room marked in the green promise current position A using the specified direction. Now how can we enable the robot to do this programmatically? One idea would be to introduce some kind of a footprint which the robot will be able to follow. Now here, a constant value is specified in each of the rooms which will come along the robot's way. If it follows the direction specified above, now in this way, if it starts at A, it will be able to scan through this constant value and will move accordingly. But this will only work if the direction is prefixed and the robot always starts at the location A. Now consider the robot starts at this location rather than its previous one. Now the robot now sees footprints in two different directions. It is therefore unable to decide which way to go in order to get to the green room. It happens primarily because the robot does not have any way to remember the direction to proceed. So our job now is to enable the robot with a memory. Now this is where the Bellman equation comes into play. So as you can see here, the main reason of the Bellman equation is to enable the reward with the memory. That's the thing we are going to use. So the equation goes something like this. B of S gives maximum A R of S, comma A plus gamma of B S dash, where S is a particular state which is a room, A is the action moving between the rooms, S dash is the state to which the robot goes from S, and gamma is the discount factor. Now, we'll get into it in a moment, and obviously R of S comma A is a reward function which takes A state S, an action A, and outputs the reward. Now V of S is the value of being in a particular state, which is the footprint. Now we consider all the possible actions and take the one that yields the maximum value. Now there is one constant, however, regarding the value footprint, that is the row mark in the yellow just below the green room. It will always have the value of 1 to denote that it is one of the nearest rooms adjacent to the green room. This is also to ensure that a robot gets a reward when it goes from a yellow room to the green room. Let's see how to make sense of the equation which we have here. So let's assume a discount factor of 0.9, as remember gamma is discount value or the discount factor. So let's assume a discount factor of 0.9. Now for the room which is just below the one or the yellow room, which is the asterisk mark for this room, what will be the V of S, that is the value of being in a particular state? So for this, V of S would be something like the maximum of A will take 0, which is the initial of R S comma A plus 0.9, which is gamma into 1, that gives us 0.9. Now here the robot will not get any reward for going to a state marked in yellow. Hence the R S comma A is 0 here. But the robot knows the value of being in the yellow room. Hence V of S dash is 1. Following this for the other states, we should get 0.9. Then again, if we put 0.9 in this equation, we get 0.81, then 0.729, and then we again reach the starting point. So this is how the table looks with some value footprints computed from the Bellman equation. Now a couple of things to it is that the max function has the robot to always choose the state. That's give it maximum value of being in that state. Now the discount factor gamma notifies the robot about how far it is from the destination. This is typically specified by the developer of the algorithm that would be installed in the robot. Now the other state can also be given their respective values in a similar way. So as you can see here, the box is adjacent to the green one has 1, and if we move away from 1, we get 0.9, 0.81, 0.729, and finally we reach 0.66. Now the robot can proceed its way through the green room utilizing these value footprints even if it's dropped at any arbitrary room in the given location. Now if a robot lands up in the highlighted sky blue area, it will still find two options to choose from, but eventually either of the parts will be good enough for the robot to take, because automate the value footprints and only that out. Now one thing to note is that the Bellman equation is one of the key equations in the world of reinforcement learning, and Q-learning. So if we think realistically, our surroundings do not always work in the way we expect. There is always a bit of randomness involved in it. So this applies to robots as well. Sometimes it might happen that the robot's machinery got corrupted. Sometimes the robot may come across some hindrance on its way, which may not be known to it beforehand. And sometimes, even if the robot knows that it needs to take the right turn, it will not. So, how do we introduce this to randomness in our case? Now, here comes the Markov decision process. So, consider the robot is currently in the red room and it needs to go to the green room. Now, let's now consider the robot has a slight chance of functioning and might take the left or the right or the bottom turns instead of taking the upper turn and get to the green room from where it is now, which is the red room. Now the question is, how do we enable the robot to handle this when it is out in the given environment? Now this is a situation where the decision making regarding which turn is to be taken is partly random and partly another control of the robot. Now, partly random because we are not sure where exactly the robot might die functional, and partly under the control of the robot because it is still making a decision of taking a turn right on its own. And with the help of the program embedded into it, so a Markov decision process is a discrete time stochastic control process. It provides a mathematical framework for modeling decision making in situations where the outcomes are partly random and partly under the control of the decision maker. Now we need to give this concept a mathematical shape, most likely an equation, which then can be taken further. Now you might be surprised that you can do this with the help of the Bellman equation with a few minor tweaks. So if we have a look at the original Bellman equation, v of x is equal to the maximum of r s comma a plus gamma v of s dash. What needs to be changed in the above equation so that we can introduce some amount of randomness here. As long as we are not sure when the robot might not take the expected turn, we are then also not sure in which room it might end up in, which is nothing but the room it moves from its current room at this point. According to the equation, we are not sure of the s dash, which is the next state or the room, but we do know all the probable turns the robot might take. Now, in order to incorporate each of these probabilities into the above equation, we need to associate a probability with each of the turns of quantify the robot. If it has got any x percentage chance of taking the turn, now if we do so, we get ps is equal to the maximum of rs comma a plus gamma into summation of s dash ps comma a comma s dash into v of s dash. Now the psa and s dash is the probability of moving from room s to s dash with the action a, and the summation here is the expectation of the situation that's the robot incurs, which is the randomness. Now let's take a look at this example here. So when we associate the probabilities to each of these turns, we essentially mean that there is an 80% chance that the robot will take the upper turn. Now if you put all the required values in our equation, we get v of s is equal to maximum of r of s comma a plus gamma of 0.8 into v of room up plus 0.1 into v of room down 0.03 into room of v of room left plus 0.03 into v of room right. Now note, the value footprints do not to change due to the fact that we are incorporating stochastically here, but this time we will not calculate those value footprints. Instead, we will let the robot figure it out. Now, up until this point, we have not considered rewarding the robot for its action of going into a particular room. We are only awarding the robot when it gets to the destination. Now, ideally, there should be a reward for each action the robot takes to help it better access the quality of the actions. But there is no need not to always be the same. But it is much better than having some amount of reward for the actions than having no rewards at all. And this idea is known as the leaving penalty. In reality, the reward system can be very complex, and particularly modeling spares rewarding is an active area of research in the domain of reinforcement learning. So by now we have got the equation. So what we are going to do is now transition to Q-learning. So this equation gives us value of going to a particular state taking the stochasticity of the environment into account. Now we have also learned very briefly about the idea of leaving penalty, which deals with associating each move of the robot with a reward. So Q-learning processes and the idea of assessing the quality of an action that is taken to move to a state rather than determining the possible value of the state which is being moved to. So earlier we had 0.8 into v of s1, 0.03 into v of s2, 0.1 into v of s3, and so on. Now if you incorporate the idea of assessing the quality of the action for moving to a certain state, so the environment with the agent and the quality of the action will look something like this. So instead of 0.8v of s1 will have q of s1 comma a, 1 will have q of s2 comma a2, q of s3. Now the robot has 4 different states to choose from, and along with that there are 4 different actions also for the current state it is in. So how do we calculate q of s comma a, that is the cumulative quality of the possible actions the robot might take? So let's break it down. Now from the equation v of s equal maximum of a are s comma a plus gamma summation s dash p s a s dash into v of s dash. If we discard the maximum function, we have r s of a plus gamma into summation p and v. Now essentially in the equation that produces v of s, we are considering all possible actions and all possible states from the current state that the robot is in, and then we are taking the maximum value caused by taking a certain action, and the equation produces a value footprint which is for just one possible action. In fact, we can think of it as a quality of the action. So q of s comma a is equal to rs comma a plus gamma of summation p and v. Now that we have got an equation to quantify the quality of a particular action, we are going to make a little adjustment in the equation. We can now say that V of S is the maximum of all the possible values of Q of S, comma A. So let's utilize this fact and replace V of S dash as a function of Q. So Qs comma A becomes R of S comma A plus gamma of summation P S A S dash and maximum of the Q S dash A dash. So the equation of V is now turned into an equation of A, which is the reality. But why would we do that? Now this is done to ease our calculations because now we have only one function Q, which is also the code of the dynamic programming language. We have only one function Q to calculate, and R of S comma A is a quantified metric which produces the reward of moving to a certain state. Now the qualities of the actions are called the Q values, and from now on we will refer to the value footprints as the Q values. An important piece of a puzzle is a temporal difference. Now, temporal difference is the component that will help the robot calculate the Q values with respect to the changes in the environment over time. So consider our robot is currently in the marked state and it wants to move to the upper state. One thing to note here is that the robot already knows the Q value of making the action, that is moving through the upper state, and we know the environment is stochastic in nature and the reward that the robot will get after moving to the upper state might be different from an earlier observation. So how do we capture this change in the real difference? We calculate the new Qs comma A with the same formula and subtract the previously known QSA from it. So this will in turn give us a new QA. Now the equation that we just derived gives the temporal difference in the Q values to capture the random changes in the environment which may impose. Now the name QS comma A is updated as the following. So Qt of S comma is equal to Qt minus 1 S comma A plus alpha t dt of A comma S. Now here alpha is the learning rate which controls how quickly the robot adapts to the random changes imposed by the environment. The QTS comma A is the current state Q value and Qt minus 1 S comma A is the previously recorded Q value. So if we replace the TD S comma A with its full form equation, we should get Qt of S comma A is equal to Qt minus 1 of S comma A plus alpha into R of S comma A plus gamma maximum QS dash A dash minus Qt minus 1 S comma A. Now that we have all the little pieces of Q learning together, let's move forward to its implementation part. Now this is the final equation of Q learning. So let's see how we can implement this and obtain the best path for any robot to take. Now to implement the algorithm, we need to understand the warehouse location and how that can be mapped to different states. So let's start by reconnecting the sample environment. So as you can see here, we have L1, L2, L3 to L9, and as you can see here, we have certain borders also. So first of all, let's map each of the above locations in the warehouse into numbers of the states so that it will ease our calculations. So what I'm going to do is create a new Python 3 file in the Jupyter notebook and I'll name it QLearning. So let's define the states. But before that, what we need to do is import NumPy because we are going to use NumPy for this purpose, and let's initialize the parameters, that is the gamma and alpha parameters. So gamma is 0.75, which is the discount factor, whereas alpha is 0.9, which is the learning rate. Now next, what we are going to do is to define the state and map it to numbers. So as I mentioned earlier, L1 is 0 until L9 we have defined the states in the numerical form. Now the next step is to define the actions which, as mentioned above, represent the transition to the next state. So as you can see here, we have an array of actions from 0 to 8. Now what we are going to do is define the reward table. So as you can see, it's the same matrix that we created just now, that I showed you just now. Now if you understand it correctly, this isn't any real barrel limitations as depicted in the image. For example, the transitional L4 to L1 is allowed, but the reward will be 0 to discourage that path. Or in tough situations, what we do is add -1 there so that it gets a negative reward. So in the above code snip, as you can see here, I took each of the states and put ones in a respective state that are directly reachable from the certain state. Now if you refer to that reward table once again that we created above, our reconstruction will be easy to understand. But one thing to note here is that we did not consider the top priority location L6 yet. We would also need an inverse mapping from the state spec to its original location, and it will be cleaner when we reach the utter depths of the algorithms. So for that, what we are going to do is have the inverse map location state location. We will take the distinct state and location and convert it back. Now what we'll do is we will now define a function to get optimal, which is the get optimal route, which will have a start location and end location. Don't worry, the code bit, but I'll explain each and every bit of the code. Now the get optimal route function will take two arguments, the style location in the warehouse and the end location in the warehouse. It will return the optimal route for reaching the end location from the starting location in the form of an ordered list containing the letters. So we'll start by defining the function by initializing the q values to be all zeros. So as you can see here, we have given the q value to be 0, but before that, what we need to do is copy the reward matrix to a new one. So this is the reward, and next again, what we need to do is get the ending state corresponding to ending location, and with this information automatically will set the priority of the given ending state to the highest one that we are not defining it now, but will automatically set the priority of the given ending state as 999. So what we are going to do is initialize the q values to be 0, and in the q learning process, what you can see here, we are taking I in range 1000 and we are going to pick a state randomly. So we are going to use the np.randomRand int and for traversing through the neighbor location in the same maze. We are going to iterate through the new reward matrix and get the actions which are greater than 0, and after that what we are going to do is pick an action randomly from the list of the playable action and years to the next state. We're going to compute the temporal difference, which is TD, which is the reward plus gamma into the queue of next state, and we'll take np.argmax of queue of next state minus q of the current state. We are going to then update the q values using the Bellman equation, as you can see here. You have the Bellman equation and we are going to update the q values, and after that we are going to initialize the optimal route with the starting location. Now here we do not know that what the next location is yet. So initialize it with the value of starting location. Now we do not know about the exact number of iterations needed to reach the final location. Hence, the while loop will be a good choice for the iteration. So when you are going to fetch the starting state, fetch the highest q value penetrating to the starting state. We go to the index or the next state, but we need the corresponding letter. So we are going to use the state to locate functions we just mentioned there, and after that we are going to update the starting location for the next iteration. Finally, we will return to the root. So let's take the starting location of n line and n location of L1 and see what part we actually get. So as you can see here, we have L9, L8, L5, L2 and L1. And if you have a look at the image here, if we start from L9 to L1, we get L8, L5, L2 and L1. That would yield us the maximum value of the maximum reward for the robot. So now we have come to the end of this Q-learning session. So this is all about our machine learning. If you have any doubt of this machine learning full course, you can ask me in the comment section. And for your comfort, I will upload a single video of this machine learning course with the timeline. Now in the next session, we will discuss machine learning projects. So thank you so much for watching video.